We're going to start this week with another of our basic quadrilateral formulas, and this is the last of them, and that is the area of a kite. Before we get into that, I wanted you to know that we are going to do our first individual formative quiz tomorrow, and it will be tomorrow is when we're going to be doing it. It will be on sections 11.1 through 11.3. But this quiz is already posted in Schoology. So if you finish today, you feel like you have a good grasp of it, then you can go ahead and start the quiz. Now, there will be an honor code at the top of it. It is no note, and I just have to take you on your word for that. So you do have to check the honor statement at the top of the quiz and do it on your own work without the help of anyone else. So that will be our assignment for tomorrow. Please let me know, ask questions if you have questions on content before that. So let's go ahead and get started into areas of kites. What we have seen so far with the area of a kite is that or with the areas of our quadrilaterals so far, is that they have special features, and that goes into our area formulas. With kites, what we care about mainly is, besides the congruent sides, is the diagonals. So I'm going to go ahead and draw in the diagonals. Now with this kite here, we're going to assume, based on the way that it's drawn, that where I'm marking them currently are where the two pairs of consecutive sides that are congruent are. The diagonal that connects the intersection of the non-congruent sides, so i.e., that diagonal gets bisected by the other diagonal, and then we know that they are perpendicular. So the longer diagonal is the perpendicular bisector of diagonal i.e. So what we're going to do is we are going to derive the formula. So for diagonal kt, what we're going to do is we are going to say that this diagonal is diagonal 1. And for my other diagonal, i.e., we're going to say that that is diagonal 2. And then as we go to, we're going to derive this formula today. So I'm not just going to give it to you. And as we go to derive this, what I want you to think about is, what do we have here that we already know? Well, what I notice is that I have a triangle. It's not necessarily a right triangle or anything special, but I do have a triangle. And as I think about how these diagonals relate to the pieces, diagonal 1 is the base of the triangle. And then when I look at the portion of diagonal 2 up here, half of it is the height of this triangle. I know it's the height because it's perpendicular. So that means it's the height of this triangle. Well, how many triangles do we have in this kite? We have 2 of them. So if I figure out for one of these triangles, the area is 1/2 base times height, well, that's 1/2 of diagonal 1. And then we have an issue. We don't quite know what this part is, but we know it's half. So we'll call this half d2. So this is times the height of 1/2 diagonal 2. If I multiply these pieces together, 1/2 times 1/2 becomes 1/4. And then that's diagonal 1 times diagonal 2. So one of these triangles is 1/4 the product of the two diagonals. Well, in the kite, we have 2 of them. So that means that I still have no clue how long these diagonals are, but for my kite, that makes the area 2 times the triangle. So that's 2 times 1/4 diagonal 1 times diagonal 2. 2 times 1/4 is 1/2 diagonal 1 and then times diagonal 2. And now I have just written a formula in terms of the lengths of both of these diagonals, and I figured out that for a kite, that has to be half of the product of the diagonals, 1/2 d1 times d2, and that's going to come and be our formula here. So for the for the kite here, we don't care about the height of it. We are not going to drop a height between the sides because it can differ, and so that's not consistent. But we have figured out that the area is going to consistently be 1/2 of diagonal 1 times diagonal 2. So we don't really care how long the sides are as long as we know how long the diagonals are. As we start to go back and think about our quadrilateral families, there are a couple of shapes that are in both the parallelogram and the kite families, and that's a rhombus and a square. And so that means that for a rhombus or a square, you could either use the parallelogram formula. You could use that the area of the parallelogram is base times height. Or if it's more convenient, maybe you know more about the diagonals, you could use the kite formula, that those shapes you can do the product of their diagonals. Now, This doesn't work for rectangles and it doesn't work for general parallelograms because they're not kites. But any shape that are also kites, we can use both. So let's look at a couple of examples here. From number 1, find the area of the kite shown at the right. So we know a couple of pieces. First is that we know that the area of a kite is 1/2 diagonal 1 times diagonal 2. So do I know the length of these diagonals? First, let's figure out which of the pieces will be the bisected part. That's going to be the section that's 12. So its little piece down below here, we know that this is going to be 12. So that means that we'll call it diagonal 1. It's arbitrary which one is which. That makes this diagonal 24. Now, with the other diagonal 2, I cannot just double it. This piece is not congruent to the piece that's 15. So instead, we have to use our other knowledge of kites. And the next piece that maybe we can make a connection here is that the diagonals are perpendicular. And we've done this before where we found these pieces of the diagonals. So if I call this x, I could use Pythagorean theorems or what I know of triples to find this. So that makes x squared plus 12 squared equals 13 squared, or hopefully you recognize this as a 5, 12, 13 triangle. So that makes this piece come out to be 5. So that makes diagonal 2 have a length of 5 plus 15, or a length of 20. So now as we go back to our formula, that makes the area 1/2 of 20 times 24. And I'm just for easy mental math, I'm going to take half of 20, which is 10. 10 times 24 is 240. So that gives this an area of 240 units squared for our kite. So you'll see this come up a lot where we'll double the half of the piece of the bisected diagonal. We use Pythagorean theorem for the other piece. We could have also done that over here with the 15 if we had known this side length, but we don't. So that is our first basic application of the kite formula. Let's look at the next one. In number 2, they tell us that the diagonals of a kite are in a ratio of 2 to 3, and the area is 27 square feet. So if you are someone who likes to visualize this, let's go ahead and draw out our kite. And then as I connect my diagonals, the longer diagonal will be the diagonal that doesn't get bisected. The shorter one is the one that does. And so that makes my shorter diagonal. When we think about ratios, remember that this is where we add in our unknown variable x. So this diagonal that's shorter would have a length of 2x. The other longer diagonal would have a length of 3x. So now I know the area is 27. I could apply that to my formula. Area is 1/2 diagonal 1 times diagonal 2. Well, we can fill in a with 27. We could fill in one of the diagonals with 2x and the other diagonal with 3x, and now we've set up an equation with a variable and no other missing pieces. So now as we multiply this, this makes 27 of 1/2 times. Now when I multiply 2x and 3x, that becomes 6x squared. X times x is x squared. This becomes 27 is equal to half of 6 is 3, so that becomes 3x squared. Divide by 3 to get that x squared is 9. Lastly, take the square root. That gives us that x is 3. Now remember that this is not our answer. We go back and ask us how long are the diagonals. So in this case here, now I just need to multiply those values that I found by 2 and by 3. So that makes one of the diagonals 2 times 3, which is 6. That makes the other diagonal 3 times 3, which is 9. And they told us that it was square feet, so we do have units. So that makes it 6 feet and 9 feet for our diagonals. All right, last one. The next one, we haven't seen a rhombus yet, and we are going to see that in this problem. Find the area of a rhombus inscribed in a circle if one of the diagonals of the rhombus is 10. So let's go ahead and start. And so we need to first start with our circle. Remember that inscribed means inside, and so I need to make sure all 4 vertices are on the circle. So I'm going to try my best. And it looks like in order to make these sides equal, this is about the best I can do. So remember what we know about a rhombus is that a rhombus is a kite. So that means that the diagonals are perpendicular to each other. It also is a parallelogram, and we know that all sides are congruent. So I know that all four sides of this shape are congruent. I'll put this, the center of my circle at the dot there. So I know one of the diagonals is 10. So now as we think about what we know or what we could figure out, because it's a kite, it would probably make the most sense, since I know one of the diagonals, to use this idea that the area would be 1/2 of diagonal 1 times diagonal 2, but I am missing the other diagonal. So now I want you to think about what you could do, what you could figure out. Remember that in a rhombus, the diagonals are not necessarily congruent, so we don't know that the other diagonal is 10, but we've inscribed it. If you have not thought of anything to do yet, I want to take you back to the story of rectangle. This was the inscribed parallelogram. Remember, the conclusion of the story was that if a parallelogram is inscribed in a circle, it became a rectangle. So a rhombus is a parallelogram. So that means that we can trace that through, that this is not just a rhombus, it's a rectangle. But more than that, what is a rectangle that has all four sides congruent? Well, that is a square. So that means that this guy here is a square. What do we know about squares and rectangles? We know that they have congruent diagonals. And that is the key to solving this through, meaning my second diagonal would be 10. You could, at this point, you could figure out the area of a square. You could find the side length and do side squared, but why do that? We already know the diagonals. That means that the area will be 1/2 of 10 for the first diagonal times 10 for the second, which gives us half of 100, which gives us an area of 50 square units. So that is it for our section on kites. The big idea, if you haven't picked this up, is that we need to know pieces about the diagonal. They are perpendicular. We can use Pythagorean theorem to figure this out. We also can use this formula for other special quadrilaterals like rhombuses and squares, but these connections and knowing our different types of quadrilaterals is going to come in and be